rather good afternoon. I would like to recapitulate what we discussed in the last session. So, in the last session, we discussed that where all carbon is getting consumed in an integrated steel plant. So, in an integrated steel plant, we when we say that, we talk about the classic route of blast furnace BOF route. We talked about increase in growth potential, current situation, and the future situation. And we saw that we'll continue with this classic route for quite some time. And there is potential of reduction of CO2 in the classic route itself. And another factor that we talked about is that this has to be economical solution for wider acceptability across the industry, because all businessmen who put up the integrated steel plant rightly look at the investment in terms of the returns. Nobody would like to put their money on a losing platform. Uh, There, with that view in mind, we saw where all carbon is getting consumed, and we saw that the biggest consumer of carbon is the blast furnace. But apart from that, there are two more places where the carbon is getting consumed. Next to the blast furnace is the sinter plant for sinter making. We do consume the coke grease and plus anthracite or simply coke grease. Or sometimes we also use pet coke there, petroleum coke. And in the pellet plant, we consume carbon in a smaller quantity, something close to 10 kg per ton of the product. So that's a small consumption, but nonetheless, this is the consumption. So we saw these are the three places where the carbon is getting consumed. We apart from that, we also saw that there is a and wherever there is a carbon consumption, ultimately that is going to be released as CO2 wherever it is, whether it is in blast furnace or in the LD shop or any other shop, because um, we saw that carbon gets oxidized into carbon monoxide and carbon dioxide. Carbon monoxide has got the calorific value and therefore is a good gaseous fuel, and we should tap the potential of that. Now, apart from that, we also saw that there is a carbon dioxide generation from the calcination of the carbonates. So we do use the carbonates in form of the fluxes. So the source of carbonate is the limestone, like CaCO3. So when we calcine this, then we get CaO and plus CO2. So this is a direct emission of CO2, and this CO2 goes through the chimney. The second source of the direct emission of CO2 is the calcination of magnesium carbonate, which is MgCO2. This route, this thing, Mg magnesium carbonate, is coming from the dolomite or let's say the pyroxenite or serpentine or any other olivine kind of fluxes that we use. And this we use for the sinter making directly, or we calcine the lime and dolomite for the LD shop uses. So there also it is being used as a flux, and there is direct emission because of the calcination. There is a direct emission of CO2 from there. So having understood this, and today we are going to talk about like if we are using carbon, and if blast furnace is the biggest consumer of carbon, then how and where it is being used. So part of that we talked in the last session, and where we saw that at least 42 to 46 kg per ton of hot metal carbon goes along with the hot metal itself, because hot metal dissolves some amount of carbon, and that is again getting oxidized in the steel making shop. Steel making shop means EOF that we talk about. So there, after oxidation of this carbon, it releases carbon monoxide and carbon dioxide. So because carbon monoxide has got a calorific value, therefore the LD gas has got a calorific value. Now, another factor that we saw in our last is that if carbon monoxide gets oxidized in presence of oxygen, whichever manner we oxidize it to CO2, then it releases heat, and that is 1 cubic meter of carbon monoxide will generate 3014 kilocalorie of heat. Now, we also saw that hydrogen also, if it gets oxidized, then it generates heat. And that heat is 2570 kilocalorie per cubic meter. So both of the gases, they do generate, albeit hydrogen generates lesser amount of heat, the carbon monoxide generates a little more amount of heat. Now, so this is what we talked in the last session. So today we are going to talk a little in greater detail in the phenomenon which is happening in the blast wall. So because that is the biggest consumer of the carbon, that is where we give the maximum amount of carbon. When we say the maximum amount of carbon in the blast furnace, that is coming from, like we saw partly in the last session, it is the biggest amount is coming from the coke. And that, if we look at the coke, it has got two components. One component is the carbon itself, and another component is the ash. Okay, so ash doesn't have any calorific value, it doesn't generate CO2. However, the carbon, once it is getting consumed in the blast furnace, somewhere or other it will generate. Another source of carbon in the blast furnace is coal injection. So we say PCI, pulverized coal injection, or simply coal. Now, in the coal injection, if we look at, there are three components. One component is ash, another component is direct carbon, and the third component is the volatile material. Volatile material, depending upon coal to coal, has got slightly different chemistry, but nonetheless, it has got varying between 32% carbon to 38% of carbon in the volatile. And that carbon is in form of direct CO or is in form of hydrocarbons. So hydrocarbons, once we say hydrocarbon, it may be CH4, a combination of these CH4, C2H2, and the other form of, let's say, TXHY. So now if you have got this CXHY and carbon monoxide, then ultimately that is going to get oxidized within the blast furnace and will get out of the top as either CO or CO2. So this is also a contributor of the carbon and therefore contributed to CO2 emission. So if now today I'm going to just show you briefly a sketch of blast furnace. This is the hand-drawn sketch, nothing fancy, but this is to explain you the phenomenon which happens in a blast furnace. This is a rough sketch of blast furnace where we charge the burden. Burden means coke and the metallics. And the metallics would mean sized ore plus sinter plus pellet. I mean, you may not have pellet in all the plants, you may not have sinter in all the plants, but a combination of these. Sized ore plus sinter plus pellet, wherever, whatever is available. So that is charged from the top. And they are charged, they are not mixed. Only nut coke is mixed with, nut coke means a small coke, the size of which is less than 10 millimeter. That is known as nut coke. So nut coke is mixed with the metallics, and metallics means sized ore plus pellet plus sinter. So that is mixed. Other than that, the sized coke is never mixed with the metallics. So they are forming the layer on the top of the burden. These are forming layers. So the hatched portion, you can see, we charge coke, and below that or before that we charge the metallics. And metallics means ore, sinter, and pellet, and plus some amount of fluxes or nut coke and or nut coke. And below that also we have coke. So the alternate layers of charging takes place at the. So this is a rough sketch of the blast furnace, and we were talking about the layers of the burden. So as you can see, the charging of the material takes place through the top. So on top we have alternate layers of coke and the metallics. Metallics means anything that is containing Fe. So which means that when we say metallics, it means sized ore plus pellet plus sinter. Wherever pellet is not available, then it is sized ore plus sinter. Where the sinter is also not available, then it is sized ore plus fluxes. Also in the metallics, small coke, which is known as nut coke, is also mixed. And they are charged in the alternate layer like it has been shown here. So this is important to understand that they are charged in layers and they are not mixed together. Now, as the material descends down, then you can see the layers here also. That will be forming the layer. However, since the dia here at the bottom portion, dia increases, the layer thickness comes down. Whatever is the layer thickness at the top, that comes down as it descends down. Then, as it comes down, then you can see inverted V kind of stuff that I have drawn here. So the top line of that is the softening line, and the bottom line here is known as the melting line. So when we say melting line, then all the material, all the metallics have molten along this line, because below that you won't find the metallics, means ore plus pellet or whatever metallics that we have charged, you won't find that in the solid form, because all that gets molten at this level. So, and this melting temperature depends upon the kind of ore that we have used. Now, for the time being, let's understand that this is the melting line. Below that, we have got the deadman coke. And this is whatever, like you can see, the hashed portion. As it is coming down, just take from the top. The hashed portion, as it would come down, then there would be some amount of coke which will get released, because to maintain the shape, because there is no support from the metallic burden. Metallic burden is supporting the thing which is above this. So if this is getting molten, then the coke also falls from here. Now coke has got two properties here. One is that it is supporting. For example, say till now that we have talked about, now let's understand that coke does not melt, because the melting temperature of coke is more than 3000 degrees Celsius. So therefore, and we don't encounter that kind of temperature here, and therefore coke does not melt. And it is the only thing that remains solid. So whatever coke is left out till this point, that falls and joins the dead man coke. Uh, Here, you can see the small thing that I'm showing you. This is the two-air, and through the two-air, we inject hot blast. So blast is basically air or enriched air at high pressure. So it may have oxygen enrichment, it may have some amount of humidity that is contained here. Plus, we also inject pulverized coal at this very level. So as we inject the pulverized coal, that is also a source of carbon, like we said before. So here in front of 2, what do we have? We have the carbon which has fallen from the top, and it is in form of coke. We also have the carbon which is coming from the PCI, and the oxygen from the hot blast, which is blast may be enriched, and therefore the blast may not have only 21% of oxygen. It may have, if it is enriched by 6%, that means the blast will have 27% oxygen. If it is enriched by 8%, in that case the blast will have 29% of oxygen. So this is what we say, that hot blast. Now, along with that, the PCI is also present here. So, two things happen here. Now, because of the high temperature, the volatile material from the coal that gets separated. And this is an endothermic reaction because it absorbs some amount of heat to liberate the volatile material. Now, the oxygen that is available from the blast, that oxygen, let's say, oxidizes the carbon which is coming from the PCI, the carbon which is coming from the coke. And since this oxygen is much lower than what the carbon that is present in front of it, for this blast, you can assume that there is infinite amount of carbon, and therefore the oxidation does not take it to CO2. It forms only CO. And so in the Bosch region, that this is the void kind of region that we have, what do we have? Nitrogen. Because why nitrogen? Because it is coming from the blast. The common air which has been compressed has contained the nitrogen. So nitrogen will be there. Then the carbon monoxide, because the carbon that is coming from the coke and the carbon which is coming from the PCI, these two get oxidized here in form of carbon monoxide. Apart from that, you may have we may have humidity, and since we have humidity, that again gets broken here, C plus H2O, and therefore it generates CO as well as hydrogen. Apart from that, the PCI also has got the volatile material, has got direct hydrogen, so that hydrogen also gets accumulated here, and the hydrocarbons also break into the CO and hydrogen. So we have only these three gases here in the Bosch: nitrogen, carbon monoxide, and hydrogen. Now, out of this, nitrogen is the inert gas because it doesn't react with anything else. However, the carbon monoxide and hydrogen, these are the two gases which are very useful. Why, I say very useful, that means they are very useful for the reduction. So these gases ascend to the top while the burden is coming down. Now there is a counter current reaction here. The counter Now this is a counter current reactor. So two things happen here. As the gases will go up, what will happen? It will exchange heat. So once I say that this exchanges heat, that means the burden gets heated at the bottom. Whatever burden that we have, that gets heated to the maximum. as the gas ascends up, then it will, because it has lost heat, so the temperature at the top will be much lower than the temperature that is exhibited at the bottom. The burden is coming down, and therefore this is the first thing, that the burden gets heated. It and the temperature at the top is the minimum, and temperature goes on going up as the burden is descending. So is that understood? So first phenomenon that we have seen, that is the heat transfer that is taking place within the blast. And what is the source of the heat? The source of the heat is the carbon oxidation in front of the 2 air. Carbon oxidation means what? C is getting oxidized to carbon monoxide, and in the process, every kg of carbon, once it gets oxidized to CO, then it generates a heat of 2450 kilocalorie per kg of carbon. So that is what gives the heat. However, there are two sinks of the heat as well, and the sink of the heat here is the humidity decomposition. And what is humidity decomposition? C plus H2O turns into CO plus H2. So humidity gets decomposed into hydrogen plus CO, and this is severely endothermic reaction, and therefore it absorbs some amount of sufficient amount of heat in front of the tool itself. There is another sink of the heat at this level, and that is breaking of the volatile material. So once the volatile material breaks, it also consumes some amount of heat. So now, once you are familiar with this sketch, I would like to go back to the slides that I have prepared. So here at the 2 level, we did discuss the exothermic reaction and endothermic reaction. So now, how does heat gets distributed? Because this very gas heats the burden from the bottom to the top. At the bottom, since the gas is having the maximum amount of temperature, it heats the maximum, and therefore it melts the burden itself. And once we say that it melts the burden, I mean that apart from the Fe bearing element, Fe gets molten, also the slag is also molten there itself. And this, the liquid metal means Fe, and the slag, both of them permeate through the dead man core, which we saw there, and gets accumulated at the bottom. So it is important that this heat transfer is a phenomenon which happens. Let's remember that the role of the carbon, or role in the blast furnace itself, in whatever manner, we have to provide heat. That is very important, because we have to melt the metallics, as well as we have to melt the slag. So these are the this is the bare minimum. Apart from that, the heat is required to heat up the burden column itself gradually. So there is a heat requirement, and this heat is transferred to the burden, starting from the melting of the metal and going on to the top, where it simply evaporates the moisture. Okay, so this is a very, very important phenomenon which happens. So there are two things, that heating phenomenon, and the second portion is the reduction of the metallics. So once we say that this is what we, this slide, we talked about this very thing, that carbon and H2O reduction, and this is heavily endothermic reaction, and therefore any moisture that we add to the blast, or even if we are not adding steam to the blast, the atmospheric moisture is also something like say 10 to 15 grams per cubic meter, and that 10 to 15 grams is also it takes some quite some amount of heat in front of the fuel to decompose into carbon monoxide and hydrogen. Okay. Now we did talk about the PCI. So this is what it is. Let's go to the next slide. Now, so heat sources we talked about, and heat sinks are the metal and slabs. For metal, it takes some amount of heat. And if we look at the amount of heat that is required for melting, for the hot metal and slag melting portion itself, that is roughly 40% of the entire heat that we are talking about. So the melting heat, the sensible heat that is taken by the hot metal and slag constitutes of at least 40% of the heat requirement. And 40% is not a small energy that we are talking about. So it's a, very important aspect to consider. The second amount and that is consumed by the top gas. When once we say top gas, let's go back to this portion again. So this gas that is leaving the blast furnace is leaving at some temperature varying between let's say 90 to 150 degrees in a normal running blast furnace. So this gas is carrying some sensible heat, and since it is carrying the heat, therefore that's a big loss or a big energy requirement. So any energy that we are generating, we should have some amount of heat uh, lost at the top gas. Why do we need the top gas to carry heat? This is a very natural question. Why do we need it? Because in the top gas, we have got H2O. See, we had H2 at the bottom. Up that H2, part of it gets converted after the reduction of the ore from Fe2O3. As we reduce it, it gets converted into H2O. Now, so top gas has got some amount of H2O. Apart from that, the burden itself will carry some moisture. For example, say sinter may not carry a lot of moisture, but size ore certainly will have the moisture. So this moisture, because of the heat, it evaporates all the moisture that is carried by the burden. Apart from that, if the coke is not dried coke, then the coke will also have some moisture varying between 4% to 8%, and which is substantial amount of moisture. So that moisture also, because of the evaporation phenomenon, which is happening at the top quartile of the top one-fourth of the height of the blast furnace, this gets mixed in the top gas. Now, how does it matter if I have got H2O there? Now, what happens that top gas also carries the fine particles from the burden, and this fine particle uh, is having some amount of fluxes or the remnants which are coming from the center and which are having CaO or MgO. Now, CaO and MgO are excellent cementing compounds. So when I say cementing compounds, that means that if in presence of H2O, they will like to stick. So any dust separation mechanism that we have subsequent to the top gas, which is coming from the blast furnace, it will have a tendency to join them together and form a lump. And if it is forming a lump, then removal of that dust will be extremely difficult. So we would like that this moisture that is coming remains in the gaseous form. It does not condense. That is the aim. And therefore, the top gas has to have some amount of heat, and we allow that sensible heat to go from the top gas. So, is that clear? Now, we did talk about heat sink, that sensible heat just now. Then, apart from that, the moisture decomposition heat, that is at the 2L level. As we saw, that carbon reacts with H2O and forms carbon monoxide and H2. This is the endothermic reaction. So, this is another thing. The volatile material, we did talk about this. It also consumes some amount of heat. Then apart from that, there are heat losses. And heat losses are, let's say, whether it is the old furnace or the older technology where we had the cooling plate in the embedded in the refractory of the blast furnace, or even if we have the new blast furnace where we don't use a refractory, but we do use the staves which are carrying water. Now, it is the cooling water. So this cooling water, whether whether in the new form or the older form, they do carry some amount. Water gets heated, and if water gets heated, then it is that heat is a heat loss. And if we do not provide for that heat loss, then what will happen? That we'll lose the refractory if it is an older design, or we'll lose the stave because the temperature would be too high and it will melt the stave itself. Therefore, it is essential that we do remove some amount of heat. We will try and minimize, but nonetheless, there is a heat loss, and we should be aware, we should provide for that. Then the fourth is that there is, in spite of everything that we do, the shell temperature itself, you will find at different in different conditions or different wearing condition and the operating condition, the shell temperature itself will vary from a temperature of, let's say, 70, 80 degrees to a couple of hundred degrees. It does vary. And because of that, there is a radiation loss. So some amount of radiation loss also takes place here. So we did talk about all the gases. At the top, we have nitrogen, we have CO, we have CO2, because the CO, after the reduction of the oxide, the oxide, once I say oxide, that means Fe2O3, which we are charging, whether it is in form of the center or pellet or the sizor, that is having predominantly Fe2O3. So that it gets, once it gets reduced, and it is getting reduced by what? It is getting reduced by CO. So there would be CO2 there. Okay. Now we didn't talk direct reduction because that's getting deeper inside, but nonetheless, you should be aware that carbon reacts with CO2 directly and forms CO again. As the burden is moving down, the burden is having the core, if the gas that has reduced CO, that would generate CO2. So this CO2 again reacts with the carbon which is in the immediate vicinity of it and generates CO once again. This is known as direct reduction. So you will have a mix of carbon dioxide plus carbon monoxide, because this carbon monoxide that has been generated, it may not encounter burden at a certain temperature at which the reduction takes place. So if it doesn't happen, then you have the carbon monoxide directly going into the top. Okay. Apart from that, also, if the gases have not been, the CO that you produced in the burst zone, if it has not been able to reduce the oxide, then it remains as CO in the top gas. Is that clear? So we have carbon monoxide, we have carbon dioxide, we have H2, and the H2 after reduction generates H2O. Also, the burden moisture generates H2O. So essentially, the four gases: the nitrogen, CO, H2, CO2, and H2O. These are the gases which are there in the top of this. So now, which is happening in the blast furnace. One is the heating. Heating is happening only in the burst zone, which is at the bottommost portion, and in the above zone we are having reduction. See, let's let's not talk about the sensible heat which is carried by the top gas, or let's say the heat that is carried by the cooling water. But the two phenomenon, the most important two phenomenon, let's remember. First is generation of the heat, which is happening at the bottom, and the second is the reduction of the oxides. Okay, and these two are happening in series. So the carbon that you are burning, uh, is generating heat. In the Bosch zone, please do remember that hydrogen is not getting oxidized. Okay, it is remaining as hydrogen. So it is not generating any heat in the Bosch zone. Is that clear? The the heat is generated at the bottom, and the reduction is happening above the cohesive zone. Okay, so all the reduction that is happening is consuming some amount of heat. And why some amount of heat? Because you need the reduction to take place. You need certain temperature of the charge. You need certain temperature to exist, that of burden. So you need heat, and you need reducing gas. Now, in we have to determine for a particular blast furnace which is higher. See, because from installation to installation, you will find that if the heat requirement is the one which is determining the carbon requirement, then we have to provide for it. Whereas, so there will be some strategy. If the reduction requirement is higher, then we have to provide for the reducing gas there. And we have to work on that, how we can reduce how we can improve on the reduction requirement. So, am I clear? Because the two things are happening in series.
Yes. So from the understanding perspective and input, this is okay. But I was trying to just think that what are the challenges when you try to implement this in the operating blast furnace? Because there must be certain challenges. Because of that, we are not able to achieve this, fuel rate, whatever the benchmark, what you are suggesting in our operating blast furnaces.
First of all, what is happening that we get confused amongst all the measures that are required. So that is why time and again I'm trying to emphasize that we have to differentiate between the heating requirement and the reduction requirement. Because the let's say the strategy, if it is a heating requirement, if it that is becoming the predominant factor, then we have to work on the heating requirement reduction. Whereas, suppose if the reduction requirement becomes predominant, in that case, we have to work on the reduction properties of the burden. So, if I say, for example, I'll just give one example to prove this. Suppose if I have to reduce the heating requirement, then what are, let's say, the 40% of the heat goes along with the hot metal and slag. This is something that I gave a rough number. In some cases, it may be 38%. In some cases, it may be 43%, and things like. So if we have to reduce the heat requirement, then we reduce the slag rate. If I reduce the slag rate, in that case, the heat, if I reduce the slag rate requirement by slag rate by, let's say, 10%, then the heat that is going along with the slag, that heat carrying capacity, that will come down. Okay, so this is one. Second is that let's say if heat requirement is higher, then we will have to use some extra amount of PCI, okay, because that is providing for carbon and also substituting the steam. The third thing that we will do without disturbing anything else will be increase in the hot blast temperature, because that's a sensible heat which is going there. It's a direct heat. So these are three examples of increasing the heat requirement, if that is coming as the bottleneck. Whereas suppose if I have to reduce the, if reduction is coming as the bottleneck or the critical factor, in that case, what will we do? We'll have to improve the reducibility property of the bird. Is that clear?
Yes, yes, absolutely.
The two strategies may converge or may not converge. This is what I'm trying to emphasize upon. And if we understand this, then our strategies would be different in case of the requirement. We'll have to identify what is becoming critical. And if we do not identify, then our solution may not be that effective. Okay? So now we did talk about the upward gas flow and the downward burden movement. Now, here, the burden as it is coming down, I forgot to mention that the oxides are getting converted in three stages. They get converted to the metal. Fe2O3 gets first converted into Fe3O4. Then Fe3O4 again gets reduced to FeO, and finally FeO gets reduced to F. Okay, so now, reducibility, if we talk about the reducibility property, then there are at least two measures on which we'll be concentrating upon. And that is, let's say, if reducibility is bad, then uh, how do we determine that reducibility is bad? If the reducibility is bad, then we will need more carbon monoxide to reduce it within the time frame that the gas is getting exposed to the metallic. If it is gas is traveling in a certain time from the cohesive zone to the top, and within this time, it has to reduce some amount of this kind of reduction has to take place. But suppose if only 70% of the reduction is taking place, then we have to, let's say, increase the travel time. How do we do that? We can increase the top gas pressure. If I increase the top gas pressure, then the velocity of the gas is reducing. So it gets more time to reduce. Second way is that I increase the concentration of the reducing gases. Concentration of reducing gas means that I increase the partial pressure of CO, I increase the partial pressure of hydrogen in the Boss gas. If I do that, then we will have more moles of CO available and more moles of hydrogen available, and which can reduce within the given time. So, and the third and most important part is I changed the reduced. Second one is that I said that we increase the concentration or the partial pressure of carbon monoxide and or hydrogen in the Boss gas. This is what I said. Suppose the partial pressure or the concentration of CO, it is suppose it is not able to reduce within the given time of travel. The burden, let's say the burden is traveling from the top to the bottom in 4.5 hours. Now, if it is not able to reduce, then you will have unreduced material in the heart, and therefore you will lose gradually, you will lose the temperature. If that is happening, then what do we have to do? We have to provide for more reducing gas concentration. So, how do we provide more reducing gas concentration? We'll have to increase CO and hydrogen in the gas that we are generating at the Bosch. Okay, so this is increase in the partial pressure of partial concentration of CO and hydrogen in the Bosch gas. Okay, and but the best property is, suppose if I am able to improve the reducibility property of the charge, reducibility property of the burden that we are charging in the blast furnace, then uh, all these things will not be required. The burden will get reduced because it has got property that it will get reduced at a let's say lesser concentration of carbon monoxide and lesser concentration of another reducing gas, that is hydrogen. So it gets reduced very easily. Then the and this we'll talk in some greater detail, maybe in subsequent session. How do we improve the reducibility? Now, this is why this is important, because if we look at the Indian scenario, then you will find that the Indian ore, iron ore, is not the best that is available. Okay, so that's a bad news, but nonetheless, we have to, with this very ore that we have within the country, to utilize it economically. There are strategies or there are methods through which we can improve the reducibility of the charge. And if we improve the reducibility of the charge, then, and if the reduction is the constant, then we are bound to have the carbon rate reduction. And frankly speaking, this is an idea, or this is a path where I think we have tremendous potential within India to reduce the carbon. Any other question?
So actually, I have a question. When
Yeah.
there is not proper reducibility of this CO, so
Hmm.
how we get the feedback? And is there any automatic process, or we have to do
No,
it
no.
manually?
See, there is no automatic process. It is to understand. You have to diagnose it through the process parameters. One of the process parameter is that you find. Let's understand. If it is not getting reduced fully, then what will happen? That FeO, it will remain part of the burden, will remain as FeO. It will not get reduced to full Fe, and that part of the FeO will come down in the hearth. Once it comes down as FeO in the hearth, then that's an indication that we are not getting the complete reduction, and so that FeO will be available in the slab. So if you find that FeO has increased from, let's say, 0.1% to, let's say, 0.8% or 0.9%, that's an indication that the reducibility property of the burden has come down. And it's a problem that we need to address.
Okay, sir. Yeah.
So now there are two, three things that we have seen here. Uh, One is that we have seen that we need to identify whether it is the heat which is required to be improved, or it is the reduction property which needs to be improved. If heat is required to be improved, then there are strategies like you increase the hot blast temperature. If you improve the hot blast temperature, that's a direct heat import into the wash zone of the blast furnace, because the blast is carrying the sensible heat. So if you improve, let's say increase the blast temperature from 1000 degrees to 1200 degrees Celsius, there is tremendous amount of heat energy that you have pumped in there. So it should work. Okay. But if the reducibility property of the charge is the constraint, in that case, you have to work upon the reducibility. If also, let's understand, if how do you determine that you need higher heat? Because some, or you are pumping more heat than what is required. How do you determine that? We have seen in the process that gas is transferring the heat into the burden. Suppose if you do not need that much of heat, then during this heat transfer, you will find that the top gas temperature is increasing gradually. Suppose you had maintained a top gas temperature of 100 degrees Celsius, but gradually you are finding that this has increased to 130 degrees, and then it has increased to 140, and then it has gone to 160. Gradually, if it is increasing, that means you don't have need for that much of heat. So you need to, let's say, reduce the heat input. And how do you reduce the heat input? By sending less amount of carbon for oxidation. Okay, because carbon is something that is hitting the cost, and is also our greatest objective of reduction, because we are here to economically, while not hitting the industry, but we need to reduce the CO2 with the dual objective of hitting the cost.
But sir, sometimes in blast furnaces, it also do happen that
Mhm.
because of poor reducibility, top gas temperature increases. That time CO by CO2 increases, and the top gas also increases because of channeling sometimes.
Yeah, so you said it rightly, Manojji, that if you have got channeling, in that case, it is having a short circuit kind of, because it is not getting time to interact. The gas is not getting time to interact with the burden very coherently or very consistently. So the CO that is generated at the bottom goes up directly. It bypasses the burden and goes up on the top. And therefore, you have higher top gas temperature. At the same time, the burden is unreduced.
Sir,
So,
actually, sorry, sir. Actually, I observed that see, basically the top temperature at the near to the BLT when at the platform level it is around 300 degrees Celsius, normal design temperature. But many times it reaches up to 1000 degrees Celsius.
mm,
So some of the equipment gets burned because of this, and
no,
it
no,
happens several times.
no, you can't sustain the operation at 1000 degrees Celsius. If you are getting 1000 degrees Celsius, even for a period which is more than 5 minutes, then it's better that you be very careful, because it is indicating that let's say you have had a slip and you have not taken care of the parameters. Because if you have got if you experience slip, and which has let's say pushed up the temperature because the burden has collapsed, and so all the gases which were trapped in between, that will be released, and you get very high temperature in the top gas. And if that is happening, then you need to adjust the blowing parameters. You can't push up the blast to very high value in such a case. You need to go up gradually, and you need to see that you don't get into a condition once again. Any other question you have?
Yes,
No,
one
yeah.
particular question, sir.
Ah, please.
In blast furnaces, we do observe
Hmm,
certain times when our CO by CO2 ratio is less. In other words, we can say the gas utilization is more. It has CO
hmm,
reaches to a maximum
hmm,
utilized level.
hmm, hmm.
We see there is drastic decrement in the top gas temperature. So what to do then?
See, I'll cover that in detail in some other session, but just to give
Okay.
you a brief around that, uh, let's say if your top gas temperature is coming down, that's not too bad. That is something because you are losing sensible heat there. But to what extent should we go? We need to look at the relative humidity of the gas because we can't allow the condensation to take place in the dust catcher or in the cyclone that you have. Means the dry dust handling circuit that you have for the GCP, we can't allow the condensation to take place. And to avoid that, we need to look at what is the minimum temperature that we can allow without having the condensation. So we need to look at the RH value for that particular temperature. And we calculate what would be the RH at that temperature in the particular blast furnace, and based on that we fix the temperature and we try and operate slightly above that temperature. We don't need, suppose if the let's say condensation temperature is coming to 70 degrees, then we don't need to be operating at 120 degrees top gas temperature because that's a waste. It's a sensible heat waste. And to reduce the carbon, that is one of the strategies.
Okay, understood your point. Okay.